slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always
Explainer. Because today, we're demystifying something you probably walk past every single day without a second thought: scaffolding. We're going to dive deep into the extreme engineering that goes into these temporary structures and the absolutely rigorous safety culture required to prevent disasters when working at height. You might just see metal tubes right now, but by the end of this, you're going to see a meticulously designed life-saving mechanism.
So our roadmap for today looks like this. We'll cover the hazards of elevated work, the anatomy of safe scaffolding, unseen risks, rigorous safety rules, and finally, emergency planning. Section 1. Hazards of elevated work. Baseline dangers. Imagine just for a second stepping out to do your job hundreds of feet in the air. Working at height, whether that's on overhead cranes, massive chimneys, or scaffolds, presents some of the most dangerous fall hazards imaginable. It requires a level of constant vigilance that most of us literally never have to apply in our daily lives. You aren't just battling the task at hand up there, you are actively battling gravity. And look, the consequences of gravity winning, they're terrifying. We're talking about severe, life-altering risks. A minor slip or a localized structural failure doesn't just mean a bumped knee. It leads to crushing injuries, tragic fatalities, and when you combine heights with heavy industrial equipment, you introduce other massive hazards too, like high-pressure punctures, fires, and severe burns. Mitigating these hazards isn't just a nice goal, it is the absolute top priority of any operation.
Section 2. Anatomy of scaffolding. Safe structures. Scaffolding isn't just a random pile of metal tubes stacked together, right? It's officially defined as a temporary structure intended to provide safe working positions at elevations. And it must be designed and inspected by a competent person. That's someone with the exact qualifications and authority to predict hazards. Get this, a scaffold must be meticulously calculated to support at least 4 times its maximum intended load without failure. Think about that for a second. You engineer it to be 400% stronger than it theoretically needs to be, just for temporary use.
There's actually an evolution to the hardware itself. You have traditional tube and coupler systems, which are highly flexible, but they rely heavily on the skill of the erector. Then you have more modern modular systems like Cuplock and Quickstage. These are brilliant because they function almost like high-stakes industrial Lego blocks. They lock together, which provides massively enhanced stability and actually takes some of the human error right out of the erection process.
But hey, none of that top-level engineering matters even a little bit if the foundation is weak. The safety of the entire platform starts at the ground with sole plates beneath the base plates. These timber or metal barriers must cover an area of at least 1,000 square centimeters. Why? Because thousands of pounds of downward force are traveling straight through those vertical scaffolding pipes. Without that 1,000 square centimeter distribution, those pipes would just punch right into the earth like needles, sinking the entire structure.
Section 3. Unseen risks. Severe consequences.
The absolute second someone gets complacent, a scaffold transforms from a safe zone into a death trap. The major unseen hazards are everywhere. We see issues like using unsuitable or rusty materials, omitting critical barriers like guardrails, or, and this is a big one, treating the scaffold itself as a rigid structure for heavy mechanical lifting, which it is absolutely not designed for. Even an inadequate platform width can force a worker to step backward right into thin air. Often, it's the simplest things that get you. Skipping a basic pre-use trek or failing to secure the top and bottom of an access ladder leads directly to catastrophic results. An unsecured ladder slips out, objects fall, workers plunge, and lives are changed forever. It's a brutal reminder that basic physics just never takes a day off. Section 4. Rigorous safety rules, mandatory precautions. To physically prevent these falls, scaffolds must have a complete barrier system. If it's built correctly, this entirely eliminates the need for personal fall arrest equipment. That's the whole goal of passive safety. You want the environment itself to be so secure that a worker can move freely, without needing to be tied off to a lifeline.
So the geometry here has to be incredibly precise. It's not guesswork. Handrails must be exactly 1.0 meter high to catch the human center of gravity. Midwells sit exactly at 0.5 meters. Toe boards have to be at least 100 millimeters tall to prevent dropped wrenches or kicking boots from sending tools plummeting to the ground below. And the platform, it must be at least 600 millimeters wide with no gaps exceeding 50 millimeters. It is a strictly controlled, geometric safe haven. Getting to that safe haven follows a super rigid protocol. Step 1, the contractor erects the scaffold, but nobody gets to use it yet. Next, a competent safety supervisor conducts a massive multi-point inspection. Only if it passes does it get registered in the site logbook. And finally, the supervisor physically attaches a ready-to-use tag to the scaffold. No tag, no access. It's really that simple.
Section 5, Emergency Planning, Accident Management. Let's look at how all of this builds into incident investigation and emergency planning. In a tragic real-world incident from a maintenance shutdown back in May 2017 involving industrial equipment, the preliminary learning was actually kind of shocking. The standard operating procedure, the SOP, was fully available, but having safety rules printed on a piece of paper doesn't save a single life if there is a fundamental lack of understanding about hazard management or stored energy. It tells us that emergency planning is really about comprehension, not just paperwork.
When an accident does happen, safety teams deploy something called a why analysis. Just like an inquisitive kid asking why over and over again, investigators dissect the event layer by layer. Say a worker falls from a trailer. The immediate cause might be slipping, but you keep asking why. Why did they slip? Defective tools. Why were they using defective tools? And on until you hit the true underlying foundation of the disaster.
And this method reveals a fascinating and honestly often uncomfortable truth for organizations. The immediate causes, like using a broken tool or stepping incorrectly, are just the tip of the iceberg. The actual root causes are almost always a failure of the organization itself. We're talking about weak safety audits, a culture of poor standards, or weak incident investigation procedures that failed to catch near misses before they became full-blown tragedies.
So true emergency planning relies on a massive overarching safety management framework. It's not just a first aid kit and a fire extinguisher, right? It requires constant hazard identification, incredibly robust emergency preparedness, and a culture of continuous learning. Every near miss must be reported. The core philosophy here is that all injuries are preventable if the system is designed to learn from its own mistakes.
Which brings us to our final thought. The next time you walk past a construction site and look up at workers suspended safely in the air, I hope your perspective has shifted just a bit. Do you see just a mess of metal tubes now? Or do you see the rigorous engineering, the precision geometry, and the deep, invisible safety culture holding them all together? Thanks for joining me for this explainer. Keep looking up and stay curious.